Hi, everyone. Thanks for joining us today. Happy to be doing another session after quite some time of silence. But we have a series of very interesting videos coming up. Today I'm very excited to have a session that is inspired by Google Copilot, but it will go beyond that to some extent. Today I have with me Suhas Pai and Ehsan Amjadian. Both of them are very active members of our community, and they're both very, very highly regarded experts in NLP. And today we are going to talk to them about doing NLP on source code. So before we go ahead, I'm going to ask each of them to introduce themselves quickly, and then we're going to jump right into it. Please.
Hello, everyone. I'm Suhas. I'm currently a CTO and natural language processing researcher at a Toronto-based startup called Bedrock AI. My interests in natural language processing include controlled text generation, privacy-preserving NLP, and as well as neural style transfer for text. So at ACE, I have been the NLP lead for over a year and a half now, and I host a NLP paper discussion group every Sunday.
Hey everyone, a pleasure to be here. My name is Ehsan. I am presently the Director of AI and Technology at RBC, Royal Bank of Canada. My background is in NLP. A ton of it. Academically, I did my PhD in the field. Then industrially, we've led various initiatives in, developing and deploying, advanced NLP algorithms as well as software.
Thank you both for introducing yourself. It's really always a pleasure to chat with you about machine learning in general and NLP specifically. You both are very, very knowledgeable on that topic. So today, as I said, we're going to talk about applying machine learning and specifically NLP on source code. So perhaps you can tell us a bit about what are some of the common machine learning techniques that people use on source code and what objectives do they have, and perhaps also highlight some of the differences of applying NLP-like techniques to natural language versus formal language like source code.
There are a whole gamut of applications that have been tried recently. One of the main ones is code search. So where you have a particular query that is presented either in a natural language or in the form of a code snippet, and you want something that is similar to that, or something that is the code equivalent of what you need. So there are other tasks that are in the realm of, for example, defect prediction and bug detection. So when you can use machine learning techniques to identify features that indicate the presence or existence of security vulnerabilities or just defects in the code. You can also use machine learning techniques for test case generation, and there have also been papers where they have tried predicting type inference for programming languages, for certain programming languages. Another commonly used task is clone detection, where you try to see whether two snippets of code actually do the same thing functionally. There are also comment generation tasks, where the model tries to generate efficient and readable doc strings based on the code. There are also code repair tasks, where you can have a machine learning model suggest what changes need to be done to code in order to fix a bug that is present in it. But the most important tasks that are gaining a lot of prominence these days, it's program synthesis or code generation, or you can call it as natural language text to source code generation. So where you provide a docstring of what you need, and then the code is generated that basically is the implementation of what is specified in your docstring.
Programming languages are more regular as compared to natural languages. So in layman's term, natural languages are more rich and therefore also more noisy. So it's harder to interpret and also much more ambiguous because of the complexity that I just mentioned. Therefore, one might imagine that then maybe applying NLP algorithms on code is relatively overpowered, especially with the ones that directly target code per se. Some of the tasks that Suhas mentioned were the interface of natural language and code. We were using NLP to form representations, then generate code. Those are absolutely hard tasks. But getting to the point, one might imagine that applying NLP techniques only to programming languages is easier because of the complexity I mentioned. However, there is also less data. So when it comes to natural language, there is any corpora out there on the internet is part of our training set, especially with self-supervised learning algorithms these days. But the subset of code out there is much smaller than natural languages.
Perfect. Thank you for giving us a bit of preview to different types of machine learning and NLP tasks on source code. Recently, GitHub and OpenAI came up with what they called Coding Co-Pilot. That is a very interesting, result, and they provided this as a feature that people can use. And I've been seeing a lot of hype on the social media. But in the session, we want to really get deep down and understand how it works. So maybe for those who are less familiar with GitHub Copilot, you can tell us a little about what it is, and perhaps also then get into some details about how it works and how it manages to solve some of the challenges that prior attempts at solving this kind of problem fell short of.
All right, great question. So they start advertising it as a AI pair programmer, which I think is a fitting brand for it regarding the variety of the tasks it does. It focuses on the interface that we just Suhas and I kind of hinted towards, the NLP and natural language. Makes things very simple. Basically, it does a few tasks that you would do with the pair programmer, or want an AI do for you. So one is generate code, out of your comments. It can autocomplete your code. It can write test cases for you, and autofill the repetitive code, so on and so forth. So it's a brilliant use of natural language capabilities. And to be honest, I think it has been there in the past, but it's at least theoretically it was, but it's a great showcase of the capability.
You are right about the capability that these type of models existed for a long time, and this problem was also worked on for decades now. But I think Copilot is a vast improvement from what we have seen in the past decade. So they use Codex, that is the model that is developed by OpenAI, and Codex is based on the GPT style of language models, and it is specifically been trained on source code that is available publicly on GitHub. So I think the amount of training data, there is like 54 million public software repositories with 179 gigabytes of unique Python files, and that's like an enormous amount of data to train on. So we don't really know what the final production model of the Codex model that is being used. they only released a paper that was speaking about a paper that's like an ancestor or a predecessor of the actual Copilot model that is currently in production. And in that paper, they were speaking more about a 12 billion parameter model, which was already showing really good numbers in terms of metrics when compared to other models that were not specifically trained on source code. So you can have the GPT-3 model, which is not trained on source code at all. And they found that GPT-3 was able to solve exactly 0% of training examples from their test set that they produced. On the other hand, there's this other model called GPT-J, built by Eleuther AI, which was trained on a dataset called the Pile, but that Pile dataset contains a subset of it is comprised of GitHub code, and because of that, it was actually able to perform better than GPT-3.
Awesome, thank you so much, guys. Actually, you answered my next question. That would have been, how did they go about collecting the data, training the model, and evaluating it? But they obviously have a lot of resources for doing this kind of thing to figure out and collect a bunch of resources about how we can build something like this. We created this thing that we call recipes. Recipes are these step-by-step instructions of, for example, in this case, how you can collect the data that you need, how you can train it, and how you can evaluate it. It will also show you a little, compact concept graph of what kind of concepts you need to know about. And then you can go about learning them in any way you want, including, obviously, checking out this recipe. And there are a lot of interesting resources that we collected. There are the additional resources. You can take a look at those as well. There will be a link to this recipe in the description of this video, so you can check it out on your own terms. But for now, we want to go through these step by step and talk about how somebody, a normal person like you and I, can build something like this.
So to do something of this magnitude, you would require big data and big compute. A lot of data, basically, and a lot of compute. And when you are talking about data for this particular task, we do have public source code in the form of all these GitHub repositories. But not every GitHub repository is a candidate for training data. So there are probably some pre-processing steps that you need to take to only filter out certain repositories that are more usable for training. So first you need to determine whether you want, how many languages you want to do it for. Maybe I think it's best to start with just a single language. Generally, I think with the model that we are building at this scale, it wouldn't be a problem for the model to distinguish between two languages. You can also make it part of the prompt so that it understands that it has to generate a Python program and not a Go program. But let us consider that we only choose Python. And then we also need to think about a few different aspects, like what is the copyright? So are there any copyright issues? So for example, if you have GPL licensed source code, is there an issue with that? What about security vulnerabilities present in the source code? So you don't want your program synthesis tool to generate code that is potentially vulnerable. So I think there have been a few proposals. So that is another consideration. One more consideration would be recency. So you have code that sometimes is not backward compatible. That is not forward compatible. So let's say you have V1 of a library and no one is using that anymore because it's not supported. But if you generate code that is belonging to an older version of something, So you need more recent code. You need code that is guaranteed to be guaranteed to run, etc. So I think I can see that you have shared a tool on the screen. That is a tool that you can use to filter repositories by number of stars, number of contributors, and even the date of creation. And I think you can use this as a filter to filter out the most popular or the most important repositories or the most representative repositories for a particular language, and generate your initial training data. One more thing that you would like to do is deduplicate the data, because there are a lot of duplicates in code, because everyone is forking and cloning all the time. So you are going to see a lot of duplicates, and there has also been recent work. I think there was a paper that came recently about how deduplication of your language model's training data is very beneficial to your to the performance of it. So deduplication is at such a large scale is not trivial. So there is a library that has been released by Microsoft, and now that I recall, even Google has a similar library. But that is so these are some of the things that you can do to prepare a training data set of this magnitude.
The first thing that you need to do is to make sure you have the data in the format that you have the signal available to you, and you have the training data points available to you, such that it can be presented to any model of your choosing. We'll talk about it in a second, as one by one instances of data point and signal. Now the next step is what are the objectives that one wants to achieve? This specifically talks about code generation, so we're going to focus on that. But let's just say that there is a ton more that you can do with this. Let's say you can writing a text and then expecting your algorithm to find bugs in it, or expecting the algorithm to find threats in it. So there is, and that will change your signal. Therefore, will change, how you format your data for the training. Okay, after preparing the data for the training and formatting data for the training, you gotta pick the objective function, as I just discussed. So the task will determine your objective function. Let's focus on the text generation. Usually, text generation tasks are the subclass of generative algorithms under nowadays what we call self-supervised systems. More traditional term for it is perhaps autoregressive methods, where you look at a sequence and its history, and you generate what's going to come next, and you can treat the task as a hint towards what needs to be generated. Regardless, there is a library online, an open source version of GPT-3 called GPTJ that one could pick to train this autoregressive generative algorithm, and then you have to feed the data. So you would prepare a data loader to feed the data to the algorithm, so on, and have the training set, have the training epochs process after a certain amount of time, depending on how much compute and resource you have. A couple of considerations I would recommend is to take into account how much memory you have, how much compute resource you have, because if you you can easily run out of memory. It would take a long time, so you got to make sure your batch sizes are correct for the amount of resources you have, and also you got to track your algorithm and make sure it keeps learning. So you want the cost you got to monitor it during training. So we're not talking about evaluation, but during training you got to track and monitor your cost going down.
So how to evaluate code generation? So in general, generation tasks in NLP are really hard to evaluate automatically. You always need manual evaluation. So the automatic metrics like blue, rouge, etc. are very based on heuristics and very suboptimal. But in the case of source code generation, you can talk about functional correctness. So you can write unit tests and then just run these models on them, and if the unit tests are passed, then you can say that the model has done well on them. So there are two types of metrics. One are functional correctness metrics, and the other one is match-based metrics. So match-based metrics are traditional metrics where you just match. You have a reference implementation, and then you just try to match the degree of overlap of your generation with the reference implementation. But this is obviously very suboptimal, and so there are functional correctness data sets. So data sets like the one that is been released by OpenAI. There are several that have been released in the past few years, like apps and so on. So another interesting metric is code blue. So code blue is not just a match-based technique based on the tokens, but it also looks at syntax and semantics. So what it also does is it takes the abstract syntax tree and tries the reference implementation as well as the generated implementation and tries to find the overlap there. And it also looks at semantics, so it also looks at the data flow graphs and tries to find the overlap in that setting. So so these are some of the metrics. OpenAI also has introduced talk about a metric called as pass at k, which is basically they sample a number of answers for a particular task, and then they find the percentage of unit tests that are passed by any of those samples. So your first sample that you generate may not be the best one, but if you generate 100 samples, maybe one of them contains the answer. But you can use heuristics to actually select one from those 100. And OpenAI folks found that the mean log probability is a good measure for finding the optimal solution.
Yeah, thanks for walking us through the data collection, training, and evaluation of a model for doing source code generation. Just to wrap it up, I would love to hear your criticism of their work. Like, what are some of the shortcomings? What are some of the challenges that this work still has?
Yeah, so I think it can be a good autocomplete tool, but calling it a co-pilot is basically calling it almost like your equal, and I don't think it's anywhere near your equal. So there are a lot of limitations, and one of the main limitations basically is the model just doesn't understand things. It is just spitting out things in the form of based on what it has seen before. It's not complete memorization, but it's still not common sense reasoning. So you are going to see a lot of code that is just not framed right. It's even the performance metrics that are shown by the GitHub Copilot is not something that is actually going to make a very huge productive gain. It's productivity gain. It is also there are also problems about the type of code that it generates. So there is an interesting ethical issue that is raised in the OpenAI paper where they say, so what if the code that it generates is going to prefer certain libraries over others? That has an economic implication. So that is one part, and I think Jeremy Howard, he had a very interesting suggestion. Interesting point. And that point was that a Copilot is preventing you from learning from Stack Overflow. So if you go to Stack Overflow, you are not just getting the answer, but you are also getting reasoning about it. You are getting more detail about it. But Copilot is very lazy. It's just going to make you a worse programmer over the long run.
A few things. One is that the codex itself can cover only around 30% of the functions that can be generated out there. According to OpenAI. So it is still massive. It is, relatively. So it will. Just imagine saving 30% of programmers' time. That's still massive and a great contribution. But 70% of it is still left out there. So that's one consideration that it needs to grow. Another relevant one actually is that to train this system, they use massive compute and massive data. So it's kind of out of the budget of a lot of other developers, and that barrier to entry usually makes the development of these systems slower than they can be if you actually count on the outsourced or open sourced workforce out there. So that's another drawback. The other one is how big these models are, which also indicates the inefficiency of the algorithms used. And I'm not using it to criticize an algorithm. Obviously, these are great algorithms. It's just that they can be much more efficient. So, for example, GPT-3 has 175 billion parameters, right? And you you'd want something much more intelligent, coming out of it. So I think given the capacity, the efficiency, what these algorithms can do can really increase.
Thank you so much for sharing your criticism about the Copilot work. It's definitely, as you said, a phenomenal piece of work. But until it being actually useful and increase the productivity of the developers, there is still a bit of time and effort and progress needed. Just to remind the audience, you can check out more details about how they went about it and how we think other people can go about building something like this using the recipe that I showed to you earlier. Okay, thank you so much for joining us today. Hope you enjoyed this session. Please make sure you subscribe to our channel and hit the bell thing so that you get notifications about our videos. We will come back with more advanced and practical videos about using machine learning and everyday applications of it. Hope to see you again. Make sure to check out the link to the recipe and other links provided in the description, and hope to see you soon.